Okay, so this is the first review sheet from our final review packet. And number one is all about cost, revenue, profit, break even. So, quick refresher, cost functions have two pieces to them. They have a variable cost, which is called the unit cost. We're going to multiply that by X and add on any fixed cost, which is costs that have nothing to do with the number of units we create. They're costs that allow us to go into business. So in this case, we've got a unit cost of $15.70. So we need to multiply that by X, the number of units that we create. And then we can add on our fixed cost of $100,000, which is just what's going to get us able to open the doors. So there's our cost function. Our average cost function, we take our cost and we average it over the number of units that we make. So that would look like our cost function averaged out over number of units, and we could divide X into both terms in the numerator if we want, or we can leave it as it is. The equation for revenue is X times the price. And sometimes the price is a fixed price, and other times the price depends on the number of units that we want to sell. Then we would call this a demand function, and we'd use the P equals function. But in this case, price is fixed to be $31.50 no matter what. So our revenue function is 31.5 times the number of units that we are going to produce. We can come up with profit by taking our revenue function minus our cost function. That's always the formula for profit. And so in this case, we're talking about 3150x minus, and we need parentheses because our cost has two pieces and we want to subtract both of them. So it's 31.5x minus 15.7x minus 100,000. And these two pieces can be combined to be 15.8x minus 100,000. So that's our profit function. And then finally, break even, that occurs when either revenue equals cost, or that also means profit is zero. Because when you pull in as much money as it took to go into business, that's when you have no profit. Then hopefully, as you continue to sell units, you will create a profit. But since I have my profit function already, the easiest way to do that is to set that equal to 0. And that would mean I want 15.8x to equal 100,000. And that would mean I want x to be 100,000 divided by 15.8. So when you do that calculation, you're going to end up with a decimal answer because it's not going to go in evenly. And that means that you're going to have to think about how do you deal with the decimal. So as I divide 100,000 by 15.8, I'm getting 6329.11, and then it keeps on going. But it doesn't matter what this decimal value is. You always want to round up, because you won't have broken even until the 6,330th unit is sold. And that is going to lead you to a certain amount of money, which is your break even. 6,330, the easiest place to figure out the money is to plug it into revenue. So if you take 31.5 and you multiply that by this number of units that you're going to break even at, you will get your Y value. And that is your break-even point because it has an X and a Y. Moving on to section number 2, that was all about demand, and we created a couple kinds of demand functions. And so the particular example I have here is not a demand function, but what it is a linear function. So we're going to think about how we create a linear function. And this is a linearly decreasing function because our value of our warehouse is going to go from $2 million to $350,000 in 30 years. So this linear function has 2 points on it, and we always make our y value the money. So we're going to match 0 years, which is when time starts, with $2 million, and 30 years later with its decreased value of $350,000. And what we're going to try to do is figure out how we're going to sort of take that decrease in value and split it among these 30 years. That's what the slope does. So if we take our y1 minus our y2 and we put it over our x1 minus our x2, our slope is going to take that decrease in value, which is $1,650,000, and split it among the 30 years and give us a decrease per year. This is what that slope is representing. So, in other words, we've got a value at 2 million, and 30 years later, it's down here at 350,000, and that means that every year I'm losing $55,000. So my value of my warehouse is 2 million minus 55,000 times the number of years that I have it, which I can call X or I can call T, whichever variable you want to use. But that's how I create a linear function. And so for B, if I want to know its value after 10 years, I want to take 2 million minus 55,000 times 10. And that's what it'll be worth 10 years down the road. So it should be somewhere in between 350,000 and 2 million, and because that's somewhere between 0 and 10 years. So 2 million minus 55,000 times 10, and I'm at 1,450,000 in 10 years. So that's the idea of a linear relationship. And then inversely proportional relationship, which is number 3, is a different situation. An inversely proportional relationship, I'm going to have my demand and my price related in a way where the one is in the numerator and the other is in the denominator. That's inversely. And I have some kind of constant up top that I need to figure out. So this says the demand is inversely proportional to the square of the price. So in this case, I have to take P and square it and put it in the denominator. So this is telling me what I'm doing to P. And I need to figure out K. The way I do that is with this when statement. When the price is $5, the demand is 100 units. So what that allows me to do is temporarily plug in X equals the number of units, 100, and P equals 5, and figure out what that K is. So at some point in time, this is true. 100 equals K over 5 squared. Or 100 equals K over 25. And that's only going to happen if K is 2,500. So I figured out what K is. And that then allows me to figure out my demand function. Because I know that X is 2,500 over P squared. And that's a demand function. But that's not the kind of demand function that's going to help me get to where they want me to go, which is marginal profit and maximizing profit. So now I need to take my demand function and rewrite it as a P equals function. So the way I rewrite that, if you remember, is we crisscross across the diagonal and we say P squared is 2,500 over X, and then we solve for P by taking the square root. So P ends up being the square root of 2,500, which is 50, over the square root of X, which is the square root of X. And this is also the demand function. So I have this or this. They're both demand functions. This is the one that's going to help me finish the problem, though, because the rest of the problem asks me for a marginal profit, and when I have demand, I can get myself to profit if I can come up with revenue and cost. So revenue, I'm going to take my P, which is my demand function, times X. That's my formula for revenue. And in this case, P is not 3150, P is a function. So I'm going to take 50 square root of X times X. And that's going to simplify to 50 square root of X. So if you're still struggling with your exponents, what I did there was I subtracted 1 minus a half. So my revenue function, I turn it into profit by subtracting cost. So I got to look back up to my problem to figure out the cost. Initial cost was $500. Got to take that away. And the cost per unit was 50 cents. So I got to take that away. And that then becomes my profit function. So they asked me for marginal profit. Marginal profit is the derivative of profit. And so in this case, it is 1/2 times 50. Drop the degree to -1/2. The derivative of 500 is 0. The derivative of 0.5x is 0.5. There's my marginal profit function. And they wanted that at 900 units. So I'm going to plug 900 in. And I'm going to calculate out 25 times 900 to the -1/2. And then I'm going to take away a half, and that'll be my marginal profit. So 25 divided by 30, which is 900 to the -1/2, the square root, put in the denominator, minus a half. And my marginal profit is 0.33, repeating. So that means the profit for the 901st unit that I make is going to be 33 cents. And finally, then I can figure out how to maximize my profit by taking my marginal profit, which we said was 25x to the -1/2 minus 0.5, setting it equal to 0, and solving for x. So I'm going to factor out x to the lowest degree, and I'll be left with 25 minus 0.5x to the +1/2. And I'm setting that equal to 0. I'm getting two critical values, 0, and I need to solve this equation. Divide both sides by a half, square both sides, and I'm thinking 2,500 is probably where my profit's going to max out. But I need to check that by seeing what happens to my marginal profit between 0, which is the lowest amount of units I can make, and 2,500. So if I plug in a number like 100 into this profit function here, marginal profit, I'm going to get a positive value out. But if I go beyond to say 3,600 and I plug that into here, you'll see that goes negative. So I have maximized my profit if I make 2,500 units, and it says find the maximum profit. So I'll need to plug that back into my profit function, which was right here, 50 square root of x minus 500 minus 0.5x. So 50 square root of 2,500 minus 500 minus 0.5 times 2,500. Just plugging 2,500 into my profit function, and I will get my final answer, which is 2,500 minus 500 minus 1,250. So we can calculate that out and get $750. So that problem took us all the way through inversely proportional, going from a demand function to a revenue function, and then going from a revenue function to a profit function, finding marginal profit, and finding maximum profit. So it has a lot of different parts to it, and that's where I'm going to end this video.